Welcome to this Nextflow tutorial, Zero to Cloud, hosted by Seqera. In this little tutorial, we're going to be creating a toy pipeline, and in doing so, hopefully elucidate or clarify some Nextflow philosophies and concepts that highlight the benefits of writing a workflow in a language like Nextflow. All right. To start, we're going to be introducing Nextflow, a little bit about the language, the technology. We're going to start with a problem and slowly build up this workflow, this little Nextflow workflow. During this construction of the workflow, we're going to sort of iteratively review what we're gaining by writing this in Nextflow. We're going to run it on the cloud, a little toy on the cloud, and hopefully, if we have time, cover some automation and conclusions. So what is Nextflow? Anyone who has done modern biology understands that modern biology has become quite data intensive, and the tooling used by the sort of bioinformatics and computational biology communities is quite complicated and diverse. And that diversity is also reflected in the complexity of the workflows that are being constructed to process that data. So here on the slide above, we have a relatively modest pipeline from the NF Core community. This is an ancient DNA pipeline that takes fast queues on the left-hand side and processes them through to some reports and some output files. And this representation of the workflow is what we call a tube map diagram, in that each of the stops on this fictitious tube map is a tool or a small set of tools that take some data, run some analysis, and write some new data as output. The data sort of flows through this graph from left to right. But one of the challenges is that each of these Nextflow processes, or each of the tube map stops in this diagram, might host or might require an entirely independent software stack, like an independent software dependency tree for each of the stops. One of the challenges that Nextflow is trying to wrangle and solve is helping workflow authors and computational biologists provide independent software stacks for each of those tube map stops. So what is Nextflow? Nextflow is both a language, more specifically, it's a domain-specific language, and that it's a domain-specific language that is designed to allow you to write code in any language, be that R or Python or Bash, and orchestrate those pieces of small programs with the Nextflow data flow programming model. That is, data flows through the graph. It provides convenient tools for defining software dependencies in a variety of different formats, be that Conda or containerization technologies like Singularity and Docker. Nextflow speaks native Git. We believe that Git is the best solution for version control. It can conveniently interoperate with GitHub, GitLab, Gitea, Bitbucket, CodeCommit, all of those major providers. And when the Nextflow source code, Nextflow workflow is hosted on Git, Nextflow actually knows the workflow understands that it's hosted on Git and understands its own versioning. So in addition to Nextflow being that DSL, Nextflow is also an execution runtime, or rather, is its own runtime. This enables the workflows written in Nextflow, the language, to be executed on a variety of different backends, be those cloud backends like AWS, GCP, or Azure, or more high-performance computing backends like Grid Engine, Slurm. And of course, for development, Nextflow will run on your laptop or desktop. One of the things that has become abundantly clear to me is that, ironically, one of the hardest things about modern computational biology is that it's very easy to do computational biology. Many years ago, I was a bench biologist, a wet lab biologist, and when you're doing sort of bench biology, it's very time consuming. Preparing an experiment will require you to make media, clean glassware, set out time courses, and the experiment will run for the time course. And really, the length of the experiment is dictated by the biology of the organism you're dealing with. When you first shift to computational biology, it's very exciting because suddenly you can queue up dozens or even hundreds of experiments in a single day. But the danger is you end up with a hard drive or a networked file system full of data, different parameters, different software versions, different scripts, and it becomes very difficult to keep track of exactly how each of those pieces of data were generated. The risk is that you come to the same data 6 months down the track, and if you're unable to understand how that data was generated, it's essentially useless. If you can't reproduce the result, you might as well throw the data away. So here's an example. This is just a shell script. The specifics of the shell script are not really important, but let's say I have some shell script to do some analysis. And let's say I've run this script and I generate a result. Fantastic, the script works and I'm happy. But then I realize on the following day that I needed to change some of those parameters. So I change a parameter, I rerun the script, and I get a new set of data. And then I notice that there is an error in the script, and I fix that error and I rerun. Or I update some of the software on my system, perhaps one of the tools, perhaps in a different experiment, an entirely different experiment, I update the software. And it happens to, that same software happens to be used by my script. And then I rerun this script. Now I'm generating multiple sets of data with different parameters, different software dependencies, and different scripts. I end up with, and this is a modest situation where I have a number of output results and perhaps multiple versions of my script, and it becomes very difficult for me to tell, unless I've taken fastidious notes 6 months down the track, how each of these results were generated. And if I have new data from the lab, how would I reprocess that new data in exactly the same way to make sure my results are comparable? So in summary, the sort of problems with this, like very naive, granted, approach are that it's very difficult to know the execution history of the project, again, unless I'm taking excellent notes, which is time consuming. It's also difficult to parallelize in a portable way. I could, for example, use GNU Parallel, which is an excellent piece of software, to parallelize some of the pieces of this script, but that will only work on a single machine. If I suddenly have to use an HPC system, or I'd like to operate on the cloud, that effort of parallelization is no longer useful to me. The script doesn't know what version it is, so I couldn't, for example, have a report which included the versions of the workflow that I was using to generate that data. There's no caching of intermediate results, so if I change a parameter, I have to rerun the whole script, even if only that last step has changed. Also, the software dependencies are not defined. I'm just calling, for example, in this script, Diamond, the alignment tool. If I update Diamond on my software, on my machine, the results may or may not change. That's a worrying prospect should be a worrying prospect if you're doing or aiming for reproducible research. So let's take that, and we're going to make it easier to scale, easier to reproduce, and as a side effect, easier to collaborate. We'll talk about each of these in turn. To do this, we're going to sort of introduce a couple of really key Nextflow concepts, and we're going to build a small script as we introduce each of these concepts in turn. The first two really important concepts we're going to talk about are channels and processes, fundamental to Nextflow. So here we are talking about channels. We have a very short 4-line Nextflow script. We define a workflow and we create a channel using the fromPath method. And we pass a string as an argument, which is in this case a glob pattern. It's going to match all files in the data directory that have extension .faa. That channel.fromPath method will construct a new path, and then we pipe that into the view operator, which just prints the contents of that channel to standard output. So I'm going to run this. Great. I can see we have our data directory, and now we run Nextflow. And I run Nextflow run dot, which is the current directory. Nextflow by default will look for a main.nf in the directory you supply as an argument there. And we see 4 lines, the last 4 lines, the contents of those channels, the paths to those 4 FAA files, amino acid FASTA files. printed to standard output. Fantastic. So that's what channels are. You can think of them as like first in, first out pipes. The second really important and fundamental concept in Nextflow are processes. Processes are like units of computation, building blocks, sort of like, you can think of them sort of like classes in object-oriented programming. So it's a sort of template for a chunk of computation that you can see here on lines 4 and 5, we define an input. We're defining the sort of shape of things we expect to be provided as input. We're going to have an input channel and an output channel. And we're going to say this process expects to be given a channel where elements in that channel are a single path to a file. We also define an output channel for this process. And into this output channel, we promise to create a file called trim.faa in the script. And we're going to take that trim.faa and dump it into the output channel. And lastly, we have a script block, which defines in this case, a shell script, but it could be R or Python or Ruby, whatever interpreted language you like, which be having to be using Bash for simplicity's sake here. And we define the sort of unit of computation. We're going to take the first 2 lines of that faster file and write them to a new file called trim.faa. Of course, this is just a very toy example. We're not doing advanced bioinformatics here. I'm just trying to keep things as simple as we can just to introduce these concepts. And again, we define a workflow. We create a channel using that channel.fromPath method. We pipe that channel that's returned from the fromPath method into the process, take first lines. And remember that channel has 4 elements in it. So each of those elements in turn, each of those FAA files are going to be delivered to the take first lines process. And each time an element is delivered to the process, we spawn a task. So we're going to spawn 4 tasks, and those are going to run in parallel where possible, as long as we have enough CPUs on the machine we're running on. We're just running locally for the moment. We're not using any advanced executors like HPC or cloud executors. We're just going to run on the local machine. Nextflow will scan our machine, work out how many CPUs we have available, and spawn as many tasks as will fit on our current machine. That take first lines process, as I mentioned earlier, defines an output channel. So we're taking that output channel and piping it directly to the view process, just as we did before, which prints the outputs of that, prints the contents of that channel to standard output. So let's see what that looks like in operation. I can see Nextflow run. Great. We've had this new line here, this line that starts with B7, A7127F. The specifics of that hash we don't have to get into, which we'll talk about in just a moment. But I can see at the end of that line it says 4 of 4. So there were 4 tasks for the take first lines process that were spawned, and they all 4 executed cleanly, which is great. And you can see the contents of the channel printed to standard output. Notice, one of the really important things to notice here is that each of these trim.faa exist in their own independent directory, these long hash addressed directories. What happens is when Nextflow begins a task, it takes a set of inputs to the process, or the task rather. It takes the input, the faster file path in this case. It takes the path, and by default the modification date and the file size, and the script block and the name of the process, and hashes that all together to generate a unique fingerprint for that task. And it's that it uses that fingerprint, that hash, to address the task working directory. This has 2 wonderful benefits. The first is that it ensures that each of these tasks happen in their own independent working directories, which means that even though we're creating 4 trim.faa, those files exist in independent directories and are not going to be overriding each other. The second really lovely thing that flows from this hashing is the caching mechanism. If I rerun this process, and we're going to do that in just a second, but if I rerun this process, the inputs will be the same, the name of the process will be the same, the script will be the same, which means the hash will be the same, the fingerprint will be the same. And when Nextflow, before it begins the task, it checks the file system and says, does there exist a directory with this hash already in my work directory? And has that exited cleanly? And if it has, I don't need to recompute this task. I can just simply pick up the existing results, the cache results from the file system. You can think about the tasks, channels and processes graphically like this. So here we have this input channel. It has 4 elements. I'm going to pass each of those elements in this first in, first out pipe to the take first lines process. And as soon as an entry comes into that take first lines process, it spawns a task and then takes a new element, spawns a task, takes a new element, spawns a task, takes a new element, and spawns that last task. And all of those tasks run in parallel. Of course, in our little toy example, they exit almost instantaneously, so we can't really see that. But you'll see when you're doing real bioinformatics that each of these tasks are executed in parallel. We don't have to wait for one to finish. And as those tasks finish, in whatever order they finish, they will be emitted into the output channel. And we get a new channel with 4 trimmed.faa files in them. The second concept we'd like to talk about is task caching. I mean, I've already sort of described a little bit about that in the previous section. So let's say, for example, I'd like to change my script. I change line 11 so that instead of taking the first 2 lines, I'm now taking the first 5 lines of the file and dumping them to trim.faa. So I'm going to rerun my Nextflow script. Great, I have 4 new FAA files as expected. But let's say I realize the error of my ways and I decide to roll back, and I do actually want 2 lines in, to take the first 2 lines instead of the first 5 lines. So I would like to go back to the version of the script that I had before. I can change that script and rerun Nextflow run-resume. And notice now here we have 4 cached tasks. This is an indication from Nextflow that instead of recomputing these results, Nextflow has noticed that we've already run these computations and we can simply pick up the results from the file system. Now, I don't know about you, but I think a lot of science, or very little science, starts at point A and moves directly to the result. There's often a lot of exploration involved, and Nextflow facilitates this exploration via this caching mechanism. So you can, for example, use Nextflow as almost like an electronic executable lab notebook, where you're trying different pieces, sort of putting a workflow together and relying on Nextflow's caching to sort of keep track of what you've done and only compute results that you haven't already analyzed. The next Nextflow concept that I'd like to introduce are parameters. So we have a silly little toy pipeline here with only a single process. Real Nextflow pipelines will have many processes and much more complicated branching and mechanisms. But you can, for example, imagine a situation where you would like to expose a piece of that workflow, some parameter or switch, to the outside user running the workflow. You don't necessarily want everything hard-coded into the workflow. An example of that here is I've changed line 17 and line 3. I've switched out the hard coding of the data star.faa in line 17 to params.fasters. So now this params object is a special object in Nextflow. I'm defining a default value for that parameter on line 3. But the fact that I'm using that params object on line 17 means that I can here on the command line when I'm invoking Nextflow use --fasters and supply a new value for that from path. So here I'm just running the workflow on faster files that match mycoplasma_g. So here we have 2 faster files rather than the 4 faster files that are in the directory. I can also instead perhaps run on blob storage. So here, instead of pulling files from my local file system, I'm going to point it to an S3 bucket. Again, using a glob pattern. And notice here, Nextflow treats files on object storage as if they were local files. I can just as easily refer to files on cloud computing as I can files on my local file system, and everything simply works. This is the first sort of taste of portability in Nextflow. The really exciting portability comes when you are able to execute those tasks on AWS or GCP or Azure infrastructure. We're going to give an example of that in a second. But this first taste of this portability is referring to files on blob storage or remote locations that could also be HTTP or FTP or AZ or GCP or S3, just as easily as they were local files. Another incredibly important concept is the idea of nailing down the software dependencies for any workflow. As I've sort of reiterated a couple of times now already, and apologies for the repetition, maintaining really close control of the software stack running each of these tasks is critical for reproducible research. You don't want a system update on your laptop to suddenly affect the results of your workflows. So here, I'm going to move my head. We have the same tiny little toy workflow. I've added a new line on line 6. I'm specifying a container directive here, and I'm passing in as the argument to that container directive a URL which points to a Docker image. So key.io is a Docker image repository service, and Nextflow/bash. So that resolves to a container that I'm going to use to execute all of the tasks in this take first lines process. The other line that I'm changing is I'm creating a new file called nextflow.config. I'm adding the simple line docker.enabled equals true. This ensures that is an instruction to Nextflow to use Docker where containers have been defined. So if I run this, now it's going to run the same little process, but each of those processes are now going to run inside a Docker container, a temporary and ephemeral Docker container. And again, we get the same trim.faa results. We don't necessarily have time to look in there, but if you have time, you're invited to look in task working directories. You'll see a .command.run file, which contains all of the Docker commands that Nextflow has helpfully generated for you. But all you really need to do as a workflow author is note that you add 2 lines, one containers directive and one configuration change, and suddenly you have defined and reproducible software stacks for each of these tasks. Lastly, the portability of Nextflow has a wonderful side effect. That is, because Nextflow can operate on your laptop, run on any workflow will run on your laptop, will run on HPC or run on cloud, it means that groups of people and collaborators that perhaps are operating on wildly different infrastructure sets can collaborate on a single workflow that defines a sort of scientific and sort of interesting research, even though they might both run that workflow on different infrastructures. So a small lab group operating on a university HPC facility can collaborate and read and execute workflows that are being developed at large biotech and pharma companies. Because the workflow is a way of defining what you'd like to get done without defining how you would like to do it, without sort of the work abstracted away from the specifics of infrastructure, it means that portability is key. Or rather, it gives you this portability. So because we have this lovely sort of community aspect that falls out of the portability of Nextflow, it's important to be able to share the workflows. So let's say I upload my tiny little toy repository, and it should still be live, to github.com/robsyme/demo. I've just uploaded my 2 tiny little files. Obviously, if you're really sharing your workflows, I'd strongly encourage you to add a README, perhaps some documentation. It'll go a long way, but just for the purpose of this workshop, we are keeping things as small as possible, and we have 2 files in our repo, main.nf and nextflow.config. They're the files that we've described just in the previous slides. Now, I could, my collaborator, my friend, or perhaps myself on a new machine, or perhaps myself 6 months down the track, if I've deleted the local version of that workflow, I can still run it because Nextflow will speak native Git. So perhaps before I delete my repo, I tag it with version 1 and I git push tags. So a tag is just an annotation on a commit. And now I can run Nextflow run and then my GitHub username / the repo name, and I use the -r flag to specify the version that I'd like. and that R flag can take things like Git tags, as I've demonstrated here, but it also could take branch names. It could also take even specific commits. If you would like to lock it in and really run a very specific version of a workflow, you can pass the commit ID, the commit SHA hash, into that -R flag. And here it said launching the URL to my repo. So Nextflow has reached out to GitHub in this case, pulled the workflow locally, run the workflow. I'm using, in this case, Docker containers, so it's going to run that same workflow in a reproducible way. Lastly, the really exciting portability aspect is cloud execution. So I'm going to take my toy example and run it on AWS infrastructure. I'm going to get rid of my face again. I'm going to take that same workflow, again, hosted on GitHub still. I've had this tiny little nextflow.config file, which defines 3 configuration values. I'm enabling Docker. I'm setting the process executor to AWS batch, and I'm setting the queue to an AWS batch queue that I know exists. There are some specifics around creating this infrastructure, which are beyond the workflow today, but if you have questions, feel free to reach out to me and reach out to Seqera. We'd be happy to talk about how the Seqera platform can create that infrastructure on your behalf. But at the moment, we're just in the open source world. We're talking about Nextflow. So if I have that infrastructure, then I can just point it at that queue. And now I'm going to Nextflow run my GitHub repo, robsyme//demo. I'm going to specify the version 1.0. And the last thing is I'm going to specify work directory. Instead of running on my local file system, I'm going to give it a path to some blob storage on S3. It's going to take a little bit longer here because Nextflow is running on my local machine, but it's communicating via the AWS APIs and submitting 4 jobs to AWS batch. So each of these little jobs, these tasks, are going to run on a cloud machine. AWS the auto-scaling groups will spin up a virtual machine, an EC2 instance, run the task, and return the result to me. And I can see here that I have my 4 trims.faa files. This means that if I suddenly have a great deal of data, so perhaps I've done some development on some files, and I've run 4 samples locally, and I suddenly have 500 samples or 1,000 samples that would take too long for me to process on my laptop, I can simply spin up EC2 instances and have those run on the cloud. So my tiny little toy Nextflow script here gives us a great deal for free. It gives us automatic parallelization. Note that I never had to explicitly describe how I'd like Nextflow to parallelize these tasks. The data flow paradigm, that is data flowing through the graph from channels, through channels into processes, and then again through channels, sort of implicitly defines the parallelization of the tasks. So I never have to define the parallelization explicitly. I also get automatic task caching, as we said. If you would like to explore some parameter space or design a workflow iteratively, you can run the workflow, add process at the end, so piece together a workflow piece by piece. And you can use the automatic task caching to ensure that if you don't need to recompute results, you won't. The third thing we get for free is the workflow is portable. I can run it on my laptop, I can run it on an HPC facility, or I can run it on the cloud. My friend running on a different operating system perhaps could run this Nextflow workflow because all the containers are Dockerized, it will generate the same results. The software dependencies are locked, again, because we are using containers to define the software environments for each of these tasks. And lastly, because Nextflow speaks Git natively, it's very shareable, and we can leverage the great resources that have been built up around Git. So in essence, Nextflow makes it easy to do the right thing. Nextflow makes it easy to work quickly, so you're not sacrificing velocity, but Nextflow has your back in that it's keeping track, ensuring that your results and workflows will be reproducible, shareable, and legible. So that's one of the open source components from Seqera. There are some other open source components, including Wave and MultiQC, but those again are beyond this particular workshop. But now I'd like to move to speak a little bit about the Seqera's commercial offerings, specifically the Seqera Platform. So you've seen that Nextflow is a great tool for a single individual, perhaps to go from a proof of concept to a production level workflow running on laptops, HPC, or cloud. But perhaps you, as a computational biologist, have written a workflow and you'd like to make that available to your team, your bench biology colleagues who would be less than enthusiastic about dropping down to the command line to run your Nextflow workflow. The Seqera platform is a way of solving a number of challenges, one of which is this idea of sharing workflows with your team. So at Seqera.io, this is what the website looks like at the moment. If I log in, I'm going to be dropped down to a workspace. In this particular workspace, it's called testing inside the SciDev organization. This is just an example. You can create your own organizations and workspaces in the Seqera platform. The Launchpad is a table of pipelines, where a pipeline is a workflow, a Git repo containing some Nextflow code tied to an execution environment. So this table is currently blank, but let's say I'd like to add my toy pipeline to the Launchpad so I can use the Seqera platform to launch and monitor its execution. I'm going to click on the Add Pipeline button. I'm going to give my new pipeline a name. I can add some labels if I want. I'm going to select the computer environment that I'd like to run in this case AWS. This computer environment has been set up previously. Again, we're not going to cover that in this workshop, but contact us for details if you'd like more information about that. And when I'm happy with those defaults, I can click Add, and it'll add a new pipeline to the Launchpad. If I filter these pipelines for SLAS, I'll see we have this SLAS demonstration pipeline ready to go. So this might be useful for me. Perhaps I'm going to launch this pipeline a number of times and I just want a graphical interface, or perhaps I want to use the automation tools, which I'm going to talk about in just a second, to execute this pipeline. Or I want to make this pipeline available to my colleagues. They or I can launch the pipeline by simply clicking Launch. And it'll drop me down to a parameter selection page. These parameters are defined by the workflow authors. There's a Nextflow schema.json file, which you'll see if you go to the github.com/robsyme//demo repository. And here I'm using the Data Explorer feature to browse buckets that I have access to. And I'm adding these paths, these S3 paths, as a parameter to the workflow. So this will take a second for AWS to spin up the instances to run Nextflow and the tasks. But when I'm happy, when rather Nextflow is happy, it will begin running Nextflow, and I can drill into the specific run. Here we have some details. The runs page, we don't necessarily have time to cover all of those right now. But Nextflow is running. I can see the execution log of the task. So this is the standard output of Nextflow. We also have the log files for download. So this will look very familiar to the workflows that we've seen running on the command line ourselves. So now we have Nextflow running on the cloud, Nextflow and the tasks running on the cloud. And previously we saw Nextflow running on our laptop and the tasks happening on the cloud, but now the whole thing is happening inside of AWS. So now that we have our pipeline in the Seqera platform, we can use that to leverage some automation features to the platform, specifically the API. So the Seqera platform has a full-featured API. So if you have your own internal tooling and you would like to hook it in, you would like to use, for example, the API to queue up or trigger a run when data is available, the API is a very flexible way of doing that. We also have a command line tool, more helpful for sort of scripting, for executing Nextflow runs on the Seqera platform. With that, I'd like to say thanks and thank you for listening. And for those that attended the workshop in person in SLAS, it was great to see you. Thank you for coming. For those that are still at SLAS tomorrow, come and say hi. We're at booth 1084. I would love to talk to you a little bit more about Nextflow. If you have any questions about Seqera platform or any of the open source components of Seqera, we'd love to chat. Come and say hi. I'll see you there.